Alright, so in our bivariate internal, we are looking at scatter graphs, of course, bivariate graphs, and sometimes we see outliers in here, so I wanted to talk a little bit about how to deal with an outlier, and more importantly, really what the influence outlier is, or what influence outlier may have on the graph. So there's two different types. We've got outliers in the y direction, and outliers in the x direction. Outliers in the y direction, if you want to think about it, I've got this chunk of data, right? And I've got a point here that's just particularly high or particularly low, but it's still within the range. So within range, just high or low compared to others. So you can see this one particularly is a little bit low, so that would be my outlier, and that's why I'm calling it in the y direction, because it's literally, it's okay, it's not an outlier in x, like there's other points that have similar x values, it's within my range of x values, but it happens to be kind of unusually far from the trend for my y value. And what happens with situations with y direction outliers is that it's going to shift the trend line either up or down. So what we notice is, remember, the trend line is the computer's trying to minimize the distance between each of those points and the trend line. So with one that's pulling it really far down, that's a big thing to minimize. The whole trend line itself is going to, in a sense, shift further down to try to match that point. And if you look carefully at this, you'll notice that, currently that trend line is kind of below those first 4 points and just kind of above those last 2 points. And it's kind of looking like it's actually below these, right? The trend line is predicting low on those points, and the reason it's doing that is because it's saying, oh, but I've got to take into account for this one down below. So what happens when we get rid of this is we're going to see our equation changes slightly. So in the second graph down below, we've taken that outlier out. You'll notice the rest of the points are still the same, and that line now, it actually kind of fits through those first 4 points a lot better. See how it goes through them, versus in this case it was a lot lower. So if I'm using this trend line here, it's going to predict probably a lower value in that low range between like 3 and 4 on the x-axis. Here I see that tightens up, and you'll also notice my r value increases quite a bit, so I go from 0.84, which is still a strong relationship, down to 0.98, which is an even stronger relationship. So if I had an outlier that I knew was a mistake in the data, one thing you could do is actually take that outlier out and go ahead and redo a prediction without it to see how the prediction would change. But you have to make sure it's actually a mistake in the data and not just an unusual point, for instance, a real point, and we'll talk about that in just 1 second as well. But again, it's just this idea that if I take out that trend line, or the effect of that outlier is that it's actually pulling the trend line down. So these points are slightly higher above the trend line than they would be without it. And you could have, you know, a situation like this where my trend line might do that, and then if I had an outlier up here, the trend line with the outlier might be slightly higher. It's going to pull it upwards, and so that's what the outlier effect would be in this case. It would be pulling up, versus this one is pulling down. Okay, so if I wanted to look at an example where I can see that, if you look at the exemplar we actually gave you for health and wealth, we've got a plot of GDP per capita and the life expectancy in years of countries. And you'll notice that South Africa is an outlier, right? It's sitting a little bit unusually far from the trend. But it's within the x range, right? This is considered a y value because I have other values with similar x, right? So it goes from 0 up to roughly 90,000. So it's not sitting outside of my x values, but it is sitting unusually low from the line. So the South Africa would be an outlier here. And so you can make a comparison between the two. You can do one with South Africa and one without, and just note how it might change your values. And maybe harder to describe on a log graph, but on a linear you could look at how it changes the gradient, for instance. But this is what I mean by we have to leave it in if it is not wrong. And South Africa is in fact a real country. Those are not made up points. It does have a higher GDP per capita and a really, really low life expectancy on average compared to other countries with similar GDPs. So you'll notice if we get my pen out, if we used a similar GDP per capita, we see that there's a few other countries in here that have a much higher life expectancy. I mean, they're almost up to 80 versus South Africa is just at like 55. So that's what we're saying is unusual. For equal GDP per capita, South Africa has a really low life expectancy. And there's reasons for that. If you look at the history of South Africa and what's been going on there, there's a reason why they have the low life expectancy. So I cannot proceed with my investigation and actually leave South Africa out. I'm going to leave it into my equation. I'm going to leave and use this equation here because it is a real point. It is really valid. But an opportunity for excellence might be to discuss how it might affect your predictions. Without South Africa, how would that change your prediction? What might actually happen for that? What is the influence on it? And in here, the influence would be that it pulls my trend line slightly further down around that area, right? Because it's low, that means it's going to pull down on the trend line around that area. Maybe not everywhere throughout, but near those GDP per capita in that X range, it's going to have that influence of pulling it slightly down. And so that's something that you could talk about. So if we go back to our notes here, one of the other things that we've got to look at here would be the outliers in the x direction. So in this case, we are looking at something where most of my data is within a narrow range of x values, and I've got one that's like way off to the left or way off to the right. Right, I could do something like this where I've got all my data points. And then have one that's like over here, all by itself. So this would be my outlier in the x direction because it's further away in x value. It's outside of my range of x values. Most values are between 2 and 6 there. So what's the influence here? These ones can have a really big effect on the gradient in a way, and we call them leverage points in a way because you can imagine that they kind of torque the line up or down depending on what's going on. So by removing these, it can actually give you a totally different equation. It's much different, so it's not just that the line either moves up or down, like we had before. It's that if that's my original line, with the outlier, it might actually point it in a completely different direction or point it completely downwards. And if we look at this graph, if I was going to draw on my own line of best fit, ignoring that outlier, I might pick one that actually is much steeper than the one that they've got with that outlier. So you can see this one leveraged that line downwards. It's actually rotating and pulling the line down, so it's got a lower gradient. And that's just from looking at this. I also noticed that the points at the start are below, and then the points afterwards are kind of above, so I've got this idea that the trend isn't quite fitting. And the reason this happens is that, of course, Excel is trying to minimize that distance between these things. And so it's trying to match up all these guys, but there's only one point out to the right out here. So it literally almost decides that, oh, well, if I just get really, really close to that point, I can minimize my distance here, and it doesn't actually change the distance too much on these ones. But it really did have a big effect. So if we look at how that graph would be without the outlier, pulling it out, take a look at the difference in the equation here. I've gone from a gradient originally of just less than 1, 0.98, to a gradient of 0.17. So remember, this first equation says for every increase in 1x, there would be an increase in 0.98y. This one is saying for every increase in 1x, there would be an increase of 0.177y. So that's like twice the gradient almost. Okay, so it's increasing at a much steeper rate here, and that's kind of that idea that I was showing you here, that if I was going to do this one myself, my trend line would probably look much steeper relative to the other one if I just drew it in on my own. And this equation is confirming that. And if you pay attention to your R values, again, this is still a strong relationship, but you'll notice it's even stronger again without the outlier. But that doesn't necessarily mean that I'm going to get rid of it. If it's a valid point, I need to hold on to it. So in this case, the idea very well could be a mistake if you don't know what the context is, but if you know that this is, for instance, Norway, and those values are real, you wouldn't get rid of that as a data point. And just paying attention to this idea that you're noticing the effect on the gradient here, that it's almost twice as much without the outlier. And an example of a place for us to look at these these x-axis outliers would be something like the Kittiwakes report. So again, with that exemplar, you'll notice we've got some outliers that are sitting further out this direction. That would be a y outlier, and that would also be a y outlier. Quite a complex graph here. This would be an x outlier, and these here would be x outliers as well. Sorry, I'm getting them confused. My bad. Okay, just to clarify for everybody, including myself. That's my x range, and you'll notice that these are within that x range, but they have unusually high or low, so these are my y outlier and my y outlier. But these guys out here, they're like way off on their own. Those are my x outliers because there's nobody else out in that range. So I've got 2 points here that are leveraging that trend line quite strongly. And then I've also got these that are kind of bringing it up and down, and in a way they kind of cancel each other out. I mean, I've got y up above and y down below, and so they're kind of pulling, this one's obviously going to pull more because it's further away. But the ones of concern here would probably be my x. And part of the thing that I'm noticing here is that, again, without those outliers, what would my trend line probably be? I would probably draw something more like that through the data set, specifically because I noticed that this one goes into negative values. So in this case, these colonies might not necessarily be errors, but I could consider this idea that if I wanted to make a prediction, in those low values, currently the way I've got this thing set up, it's not going to be very good at predicting these low values. You see, it doesn't actually fit very well there. So there is the opportunity here to potentially say, well, in this case, if I got rid of those far outlying colonies, those biggest ones, I can actually get a trend line that fits through my smallest data points better, or my smallest colonies better. And so you could have a separate trend line for predicting small colonies specifically. You've got one trend line for overall, and then one here that matches slightly better for small colonies. So that's just one way to apply that and to think about it. Again, being careful to think about exactly what that outlier is and what it represents, and how it might affect your predictions. So with your outliers, oops, yes, just remember you've got your y1s that are either higher or lower compared to the relative points, and again they're going to pull your trend line kind of directly up or down in a way, just like sliding a stick along. And then when we've got these ones, the leverage points that are kind of tilt it or curve it potentially, and they're going to be effect on the gradient, so watch what they do there. Again, this one the gradient ends up being almost twice as big. So it is possible to break up your data. You might notice that you've got like males and females, for instance. So if, one of those is my males and one of those is my females, together, my trend line, I don't know, might kind of split the difference and do something sort of like this, maybe more so. Right, so it's not perfect for blue, it's not perfect for red, but that's my overall trend line. But you do in Excel have the ability to break these into separate data points. So you could get a trend line for your red to predict if you're predicting males, for instance, and you could get a trend line for your blue separately to use to predict if you're predicting your females. So those are some of the opportunities to get into excellence, and I'll put together another video that shows you how to separate out your data like that.